So the question I want to address today is the following. So suppose you have a family of smooth curves. Projective connected curves degenerating to a nodal curve. Always projective and connected. And then the question is how can we classify all the modular degenerations of the induced family of Jacobians of the smooth curves. And so this problem has been studied since the 70s, but the focus of today's talk is to classify all of the possible degenerations. So we know many of them, and we want to classify all of them, and in doing this, we discover also new ones. And now I have to tell to you what do I mean by modular degenerations. By the way, this is a talk which is inspired by two works of Pagani and Tommasi, where they consider this question. So, what do I mean by modular degeneration? So I mean the following. So definition. Suppose X is a nodal curve over an algebraically closed field. Then I want to look at find compactified Jacobians. Maybe I'll shorten this with FCJ. So if I'm compactified Jacobian is an open, connected, and proper substack. So I'll denote this by something like this of the following stack. So this is the GM rigidification of the stack of rank 1 torsion-free sheaves on X of degree D. So by this I mean I'm considering coherent sheaves on X, and then torsion-free means that I is pure, so it does not have subsheaves pure with full support. And the rank 1 means that it has rank 1 on each irreducible component, and you can say this by saying that I is generically a line bundle. And so these are the kind of sheaves I want to consider, and the degree of any such sheaf is the number for which Riemann rock holds. So by definition, I put this equal to the Euler characteristic of I minus the Euler characteristic of the structure sheaf of X. Okay, so so there is a stack parameterizing all these objects. Then any such object has a GMO automorphism, the scalar automorphism. So I remove these automorphisms, so this is okay. So let me tell you that this is okay. This stack is huge, so it's not of finite type. Nor separated if X is reusable. Okay, one step back. So if X is irreducible, then this stack is already proper. So then the unique fine compactified Jacobian is the entire stack, and the problem is trivial. So the interesting case is where the nodal curve is not irreducible. Then this stack is huge, it's not of finite type, because this degree can distribute among the reducible components, and it's also not separated. So we are looking for open and proper substacks of this huge stack. Okay, so I want to find all these substacks, all these fine compactified Jacobians, which can be put as a central fiber in this family.
Can you give an example explaining non-separatedness?
No, now, maybe later.
Can you say also just one word on rigidification?
Yeah, so if I don't consider this rigidification, then there's no hope to find a proper stack, because all the so if you have a proper substack, then the automorphism group of this guy are going to be trivial. So you have to rigidify to find this proper substack.
Is it the same as just taking families up to pull back from the base, or is
yes, exactly. Yes. Yes.
And for why not take some of the line curve or that curve? And
yes.
One family and then this with a fiber or
but that's the relative case where you have a smooth curve degenerating there, then you can twist, and then you see non-separated of the relative thing. I think Sasha was asking for the non-separatedness of the for an individual curve.
But then how do you know that it's not separated?
I know. Okay, so for example, so in this in this case here, I know that this stack it's a curve and it looks like this. So so it's a one-dimensional stack with infinitely many components, and so it does look like so you have what is the picture? So you have like a double a line with a double origin. So how do you know this picture?
Maybe I'm non-separated black hole.
So maybe I'll put this later. I didn't prepare this example. The drawing.
A non-separate line with a DM in it.
Yeah. It's infinitely many copies of P1s. Each of them has two non-separated points at 0 and infinity, and then they are somehow intersect among each other. Okay, so yes, what I wanted to say. So Yeah, this implies. Oh, by the way, this so this kind of sheaves. So from this definition, it follows that if you restrict I to the smooth locus, then this is locally free. While if you look at the stalk of I at a singular point, so at the node, then this can be either the stalk of the structure sheaf, or it can be isomorphic to the maximal ideal of the node. And this is the case where it's not locally free. And then I define the singularity of I, the set of all the nodes, such that the stalk of I at P is isomorphic to the maximal ideal. So the set of points where the sheaf is not locally free is called the singularity locus of this I. So this is a subset of the set of nodes of my curve. Yes, by the way, for position any such object, so any fine compactified Jacobian is actually a projective reduced scheme. So it's clear by the properness that it must be contained in the locus of simple sheaves, which is an algebraic space. It's the algebraic bigger algebraic space open subset of this. And then also let me add with nice singularities. And the singularities are actually products of nodes.
So what was J here? The Jacobian or the compactified? What's J here? The compactified Jacobian?
Yes.
No. And is the J compactified? The G part of J.
Yeah, this is a notation for any of these objects.
Okay.
Yeah, it's because there are many of them, so I should put some decorations, and later on I will do it. But for the moment, just if I have to find compactified Jacobian, I can call it like this. Okay, so these objects are very nice. So they are projective reduced schemes with nice singularities.
You were commenting, you said it's an algebraic space.
Yes, so the proof of this is, first of all, you prove it's an algebraic space because it's proper, and so then it must be an algebraic space. And then, okay, then this, then you can prove it's projective by using the Collar ampleness lemma. And the fact that here this curve is trivial, so you have a universal sheaf on this guy, so also this guy, and so using this you can produce a semi-ample line bundle with a quotient, so that you can run Collar semi-ampleness to prove projectivity, and then this fact about the singularities, it follows from the deformation theory of this kind of sheaves. So each time you have a singularity, then in the deformation space you will see the deformation space is also give you a contribution of a node. So if you have n singularities, then you in the deformation space, the semi-universal deformation space of this sheaf will be a product of n nodes plus some smooth factor.
So you mean one-dimensional nodes or higher dimensional?
No, one-dimensional nodes. Yes. So any singularity of the sheaf give a one-dimensional node. Okay, and this is computation that I did with Iano and Jessica, but so you can compute explicitly the deformation space of these sheaves. Okay, so
in particular, it's the local completing factor.
Yeah, in particular, it's a local completing factor. Yes. Okay, so let me now give you the following key example. So this is the example you can find
in the paper of
Pagani and Tommasi. So this is, so I told you when the curve is irreducible, the answer is trivial. So let's look at next case. So let's suppose that the curve has two irreducible components. You can assume that they are smooth. So internal nodes do not matter in this story. So assume that there are two smooth components meeting in, say, T nodes. So a curve like this is called the Vine curve. Okay, and then in this case, there is a complete classification of this fine compactified Jacobians. And so the classification is like this. So they are classified by pairs of two integral numbers, such that they add to d plus 1 minus t. Okay, this is complete classification of fine compactified Jacobians of this curve X. And this association, this bijection is as follows. So to any such pair, you associate the following object. So you look at all the sheaves in our huge stack, such that, and then you impose that the degree of the sheaf on C1 is greater or equal than N1, and the degree of C2 on I is greater or equal than N2. So by this degree, I mean some notation. So whenever I have a subcurve, in general, whenever I have a subcurve of a nodal curve, then I define the degree of I on Y to be the following. So you take your sheaf, you restrict to Y, then this may acquire some torsion. So you remove the torsion, then you get the rank 1 torsion-free sheaf on Y, and then you take its degree. That's the definition of this degree here. So, so you are looking at all sheaves such that the degree on C1 is greater or equal than N1, and the degree on C2 is greater or equal than N2. Now, this you can also reformulate in the following way. So there is a relation between these two degrees and the total degree. So the relation is the following. So the total degree of I, which is D, is equal to the degree of I on C1 plus the degree of I on C2 plus the cardinality of the singular locus of I. And so then using this relation, then you can reformulate this by saying that you are looking at torsion-free sheaves such that the degree of I on, say, Ci, for I equal to 1 on 2, this lie in the following interval. So it's the interval that starts at Ni, and then the amplitude of the interval is between 0 and and t minus 1 minus the singularity of I. So this two lower bounds using this relation, it can be turned out, so you can use these two lower bounds to give also upper bound on the degree. And so then you end up by saying that, requiring that the degree of I on Ci lies on an interval. And so the amplitude of the interval is always the same as this t minus 1 minus the cardinality of the singular locus. So for example, if it is a line bundle, then the amplitude of the interval is t minus 1, and if it is singular, then it gets smaller and smaller.
So who is t?
T is the number of nodes, the number of intersection points. And so the amplitude loading interval is the same, and what you can choose is the starting point of the interval. So these two are the two starting points of the interval for this inequality. And there should be a relation between these two starting points and the total degree you are working with.
But generic element is a line bundle always.
Yeah, the generic is a line bundle. Yeah, the smooth locus of this guy is the locus of line bundles. Okay, so this is a classification for qualified compactified Jacobians, and actually all of them arise as limits of Jacobians of smooth curves degenerating to the given curve. Okay, so this is, but this you can prove by induction a number of nodes. In the case of one node, you get a curve of compact type, where it's very easy, and then you do induction on the number of nodes by normalizing your curve to a given node.
And are they all like closures of loci of line bundles with specified multi-degrees?
Yes, 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 yes. So the locus, the open subset consisting of line bundles is always dense, and it's always the smooth locus of these gaps.
So is the normalization of this compactified Jacobians is always smooth or not?
Yes, in this case it's smooth. Yes, yes, exactly. Yes, normalization is always smooth. Yes, and it's a disjoint union of toric varieties. Okay. If the genus of the two curves are 0, then it's then this guy is obtained by gluing smooth toric variety along toric boundaries. And otherwise, there is contribution coming from the Jacobians of normalizations of the curve.
So this is in the case of two components.
Yes. Now, but this is the key example. Now I introduce the following definition. So definition. So now X is an arbitrary nodal curve. And then I say that the stability condition, V stands for Wien curves, is the following. So it's a collection of numbers that I denote by this Gothic n. So I have to give an integral number for any subcurve such that y is non-trivial, meaning it's not the empty subcurve nor the entire curve, and it's bi-connected, which means that y and the complementary subcurve are both connected. And this collection of integers must satisfy two relations. So the first is that if I look at the integer at y plus the integer at the complementary subcurve, this should be equal to d plus 1 minus the number of intersection points between y and the complementary subcurve, as in that the same relation as above. And then there should be a compatibility between, so if I have y and z, two subcurves without common components, and if I assume that both y, z, and y union z are biconnected, then there should be a compatibility, and the compatibility is the following. So the number associated to the union minus the number associated to y minus the number associated to z minus the number of intersection points between y and z. So this number here should be either 0 or minus 1. So it's very strange looking compatibility condition between these numbers. And I will comment later why we need this, and it's, that you you should put this condition. Otherwise, it's the mildest condition that you have to impose to for things to work out. And then, so if I have any such this stability condition now, I can, okay, so what's called a Vine type? Okay, so given a biconnected curve is the same thing as giving a partial smoothing to a Vine curve. So if I have this biconnected curve, then I can smooth all the nodes except those at which y and y complementary subcurve intersect, and I get a Vine curve. And vice versa, if I have a partial smoothing to a Vine curve, then I can take the closure of two components of the Vine curve, and I get two complementary subcurves that are connected. So we are really looking at partial smoothing to Vine curves, and then there we are imposing these two numbers. That's the way to think about this stability condition of the Vine type. So now if I have, this is called of degree B.
And is it true that the second condition comes from smoothed two triangles?
Yes, like if you have Y and Z, and then you have the union, yeah, there's, so this is, you think this is Y and this is Z. Yes. Moving the triangle. Okay, yeah, there is compatibility properly, yes. Okay, so then to any such object, now I associate the following. So I look at all the sheaves of degree such that, and then the condition is that the degree of I on Y is greater or equal than Ny. So I impose this lower bound, again, this is for every biconnected subcurve. So I impose this lower bound on the degree of my sheaf on biconnected subcurves. And again, the same reasoning as before, you can say this lower bound for Y and for Y complementary, for the complementary subcurve, actually you can use this to say that actually the degree of Y is in the interval that starts at Ny, and the amplitude is, as before, 0. Yes, the amplitude of the interval is what is okay, the number of intersection points between Y and Y complementary minus 1 minus the number of nodes between Y and Y complementary at which I is singular. So that's the amplitude of the interval. So what we are doing is we are parameterizing sheaves such that the degree of this sheaf on every biconnected subcurve lies on this interval. So the amplitude of the interval is always the same. And we are only choosing the starting point of this interval. Now it's clear that if you don't put any condition, then so there is some relation between the degree of I on the union and the degree of I on the two components. So if you don't, there should be some relation, otherwise this would be the empty set. And I'm thinking that this is the right condition. Okay, so so I call this fine compactified Jacobians of Vine type, or maybe the fine compactified Jacobians. Okay, so now what's the theorem? Well, theorem A. Yeah, like that. So from this definition, it's not clear, but so theorem. These are so theorem A. These are fine compactified Jacobians. So that's the first theorem. Now, example. So there is a standard way of cooking up this stability condition, and this is via general numerical polarizations. So suppose X is a union of n irreducible curves. Then, so a general numerical polarization of degree is the following. So it's a collection of real numbers, one for each irreducible components. Maybe I call E of C1 up to E of Cn. So it's a collection of real numbers such that their sum is equal to D. They sum to D. And for any pi-connected subcurve, the following number. So I can consider the sum over all the irreducible components contained in Y of the corresponding numbers. And then I can subtract the intersection between Y and Y complementary subcurve divided by 2. This should not be an integral number. Okay, so if you pick a random choice of these real numbers, then which sum to D, then this condition will certainly be satisfied. And then if you have
so don't you have any positivity in something?
no. That's why it's called numerical polarization. So of course, if you have a polarization like an M-line bundle, then you can associate to it numerical polarization, and I think you have to take the degree of each component divided by the total degree. But this is more general. You don't need any positivity assumption. And I'm claiming that to any such phi, I can associate a V stability condition. And this is the following. So what's the number associated to Y? So I take this number here, and I take the upper integral part. So this is called usually phi of Y. So I take phi of Y minus this number here, and I take the upper integral part. And I'm claiming that this is the V stability condition. So, for example, the first condition follows from the fact that if you take, without taking the integral part, if you sum this and the corresponding number for Y complementary, you get exactly D minus the number of intersection between Y and Y complementary. But since both of them are not integral, when you take the integral part, you gain one more. Then you get one. And then it's pretty easy also to check that this condition is satisfied. And you don't know if there is a 0 or minus 1, because you don't know, when you take this integral part, then you can get both 0 or minus 1. Okay, and then in this case, this compactified Jacobian is something.
Taking a general polarization, you take a non-general one. The only difference is that one.
Yes.
One
Okay.
is the coprimality.
Yes. Okay, maybe just so there should be a story for a non-fine compactified Jacobian, which should be defined as open connected substack with a proper good moduli space. And but I haven't yet worked out the details. And yeah, and there you should. So this should be called generic V-stability conditions. And for non-generic ones, then sometimes you have T plus 1, sometimes you don't have this 1, which corresponds to the case where this is an integral number or not. Yeah, but for today, just I will work with fine compactified Jacobian. Okay, then in this case, this object is something well known. This is, now I will call it the classical fine compactified Jacobian. And this kind of objects were first studied by Oda and Seshadri. Then it was realized that they coincide with, they can realize as modular space of slope stable sheaves. If you choose so remi phi, there is a polarization on your curve such that the space of slope stable or slope semi-stable object give rise to this object here. And then they also show up again later in the work of Caporaso and the work of Esteves. So that there are different methods to construct this, and so in all these works, even though the methods are different, they end up with this the same object. And I always wonder why is this the case. And now I more or less understand why. So now I give this theorem B. Okay, so theorem B. So first part, so the inclusions. So now we have, okay, we have this classical fine compactified Jacobians that we know since many years. Then there is this new class of the fine compactified Jacobians, and then there is the entire class. So I'm fixing the curve. And then there are the class of all fine compactified Jacobians of X. And I'm saying that these inclusions are strict. In general, for an arbitrary X. So one can find X for which this inclusion is strict. So here, the smallest example that I have is the following. So it's a curve whose dual graph, that's the dual graph. So here, what is really important is the dual graph of the curve. So the smallest examples where this is strict. So in this case, you need at least 6 irreducible components, and the smallest subgraph is this. So you take an hexagon, and then you join these two opposite edges. So this is a genus 3 graph that can be realized by genus 3 curve, and in this case there is one fine compactified Jacobians of Vine type which is not classical. That's the smallest example. Then, of course, I expect that there will be many more in general if the curve is complicated. many more fine compactified Jacobian of bind type than the classical ones. And here, the smallest example is the case of if you have a cycle of 3 components or higher. So let's say an n cycle with n greater or equal than 3. Then Pagani and Tommasi have classified all compactified Jacobians. And it turns out that you take this rational component, so this has genus 1. So fine compactified Jacobians are again curves, and they have classified all of them, and it turns out that they are again curves of genus 1. And but the point is that they are again cycles of rational curves. But as soon as n is at least 3, then the number of irreducible component can be a multiple of n. So if you start with, say, 3, then you can see a cycle of length 3, 6, 9, 12, and so on. And those that are of Vine type are exactly those that are isomorphic to the curve itself in this special case. Okay, and then let me say point 2 that so V fine compactified Jacobians are finite up to translation. So by this I mean the following. So there is an equivalence relation on the set of fine compactified Jacobians. So if you start with 1 and you take any line bundle of X, then you can tensor all the sheaves on that compactified Jacobian with that line bundle, and you produce another compactified Jacobian. Okay, so there is an equivalence relation given by this translation, and this class here, and therefore also this class, there are a finite number of equivalence classes, while the same example shows that this is not the case for this class here. But fine compactified Jacobian are not finite up to translation. Because if you translate, then in particular the fine compactified Jacobians are isomorphic. But here you can see cycles of arbitrary large length. So you will see infinitely many equivalence classes up to translation. Okay, so this theorem says the following. So we have found new compactified Jacobians, and yet we are studying a subclass of all fine compactified Jacobians, but it's a subclass that is manageable to an explicit classification. While I think there is little hope to classify all these objects here with this subclass, since fixing a curve, there are a finite number of them up to translation, so there is some kind of hope to get a good understanding of the how many fine compactified Jacobians of one type do we have, and if we can classify and understand all of them.
For 2 components, they're all the same.
Yes, for 2 components, exactly. For 2 components, this is we have described all of them, and they are all classical types. Yes. Starting from 3, you get this is strict, and here you need at least 6 components.
Can you describe explicitly the simplest example of FCJ, which is not FCJ?
Describing, you mean
by some degree conditions or by something?
No, again, not on the top of my head.
But you say that this is in the paper, right?
Yes, this is in the first paper of Pagani-Tommasi. They classify all of them.
Can I ask a question? I forgot to ask you from that. Is the compactification of the Picard or without cover?
Yeah, okay, so why they're called compactified? Yeah, okay, so if you look at the smooth locus, so if you have any compactified Jacobian and you look at the smooth locus, then you are going to see a disjoint union of a finite number of what is called the generalized Jacobian of your curve. So this is parameterized line bundle integrally 0, so it's a semi-abelian variety, it's a nice variety. And the smooth locus is always a disjoint union of several copies of this. This is why it's called compactified Jacobians.
So the number is fixed?
No.
Oh, okay.
Here it's fixed. For this class it's fixed. And it's always equal to the complexity of the dual graph. But here it can vary, like in this case, the number of reduced components can be n, 2n, 3n, 4n. Okay, so it can be a multiple of n.
I see. So is that true like for all the V compactified compactified, they are directional, but not the case for
What?
Is that the case that for all V compactified Jacobian, then they are all birational?
Yeah, they're all birational because they're the same smooth locus. This class here, but not this.
But no, okay.
So now the question is, okay, so why do we care? Why do we care about this fine compactified Jacobians of this type? And well, I'm saying that this provide the answer to the question I started with. So theorem C. Okay, so let now I take an arbitrary fine compactified Jacobian of X, and then the following are equivalent. The first is that this is of Vine type. The second condition is that it is okay, smoothable. Actually, there are two versions of smoothable. So one I call regularly smoothable. It means the following. So it tests there exists a regular one parameter smoothing of X. By this, I mean a family of curves over a DBR whose special fiber is the curve you start with and whose generic fiber is smooth. This is one parameter smoothing, and regular means that this total space is regular. And such that if you put over the spec R, if you put together the compactified Jacobian you started with the union with the Jacobian of the smooth fiber, you can do this union inside the stack of relative torsion-free sheaves, torsion-free rank 1 sheaves. Okay, so this is inside the stack of relative sheaves. Then this map here is proper, such that this is always it's always open, and so therefore it's always flat, but it's not always proper. And if this is proper, then we call this regular smoothable, and this happens exactly in this case. So this is one version of smoothability. Then there is a second version that I call simply smoothable. So here we are just requiring that the condition is that there exists just one regular one parameter smoothing, and here the condition is that for any one parameter smoothing, not necessarily smooth, not necessarily regular, the same thing holds. this again is proper. And so this condition is a priori much stronger than that one, but actually they are equivalent. And then there is even something better you can do, but it's again equivalent to that, is that this guy is universally smoothable. This means the following, that you can look, instead of looking at one parameter smoothing, you can look at the universal deformation space of your curve. So for the universal deformation space, so for the semi-universal deformation of X, so there will be some spec of some ring, I don't know, Rx. This is a formal power series ring, and above it there is a universal family, and such that the special fiber is your X. So that's the semi-universal deformation of X. So above this guy, then there exists, the claim is that there exists a relative compactified Jacobian. So there exists above this guy something open inside the stack of relative rank 1 torsion free sheaves. Open and therefore automatically flat, but the request is that this is proper and such that the central fiber is the guy you started with. So this object over 0 is the original fine compactified Jacobian. So it means that we can extend this fine compactified Jacobian to the semi-universal deformation space of X. And this is very important because this guy here is regular. This is again in the paper with Jano and Jessica. So now this time is the fact that the deformation factor of the pair curve together with a sheaf is formally smooth. So you can put this inside a regular space, and then, for example, then you can, using this, you can do now we have this vibration, you can apply the decomposition theorem, and then this allows you to define a perverse Leray filtration on the cohomology of this object here when you are over the complex numbers.
Okay, so can you replace this condition that it's proper with the condition that the thing on the central fiber is the closure of the thing on the general fiber, or is that not true?
No, that's never true.
That's never true.
No, the closure will be everything.
In this T of J, D.
Yes,
Okay,
yes,
the
yes,
closure
yes.
will be everything.
Yeah, the closure will be everything, yes. You can always move rank 1 torsion free sheaves. And there is a final condition I would like to mention that the condition is that this guy here is what we call of Néron type, which means the following: it tests for any regular one parameter smoothing so not only this guy is proper, so this guy here over spec R, now R is a DDR, is proper, but also, and its relative smooth locus is the Néron model of Jacobian of the generic fiber. So whenever you have a DVR and over the generic point you have an abelian variety or a torso, as in this case, there is also a canonical way of extending this to a separated group scheme over spec R, which is called the Néron model. It has a universal property. And in the case of Jacobian, this has been described by Renaud. And we are saying that this relative guy here is a compactification of the Néron model of the Jacobian of the generic curve. So in particular, it follows from Renaud results that we know how many reducible component and the Néron, the special fiber of the Néron model has, and it's exactly the complexity of the dual graph. So it follows from this that number of reducible components of this guy is always equal to the complexity of the dual graph of the curve. Complexity is the number of spanning trees of the dual graph. Okay, so this is a geometric characterization of this fine compactified Jacobian of fine type, and it answers in 3 different ways our original question. So we have found all fine compactified Jacobians that are limit of smooth curves, and so let me say that also as a corollary of this. So many of the results, so we can extend. So fine compactified Jacobians of this type share similar properties of classical fine compactified Jacobians. For example, they are Calabi-Yau varieties. So the canonical line bundle is always trivial. They are birational among themselves. So birational among themselves. But not necessarily isomorphic. So we have example of non-isomorphic fine compactified Jacobians of even classical type.
Are they derived equivalent?
Yeah, I'll come to that. Yes, they are derived equivalent. So here we need an assumption on the characteristic. If the characteristic is 0 or is greater than the genus of the curve, then we can prove that they are derived equivalent.
The geometric genus?
No, the arithmetic genus. So yes. All right.
So how do you prove the second argument? How is this proved?
Yeah. Okay. So so you consider 2 of them, and then on the product, there is a way of constructing a Poincaré sheaf, which is not a line bundle anymore. It's only a sheaf, Poincaré sheaf. And this uses so you embed your curve inside a smooth surface, and then there is a lot of work done by Arinkin that uses the isospectral inverse scheme of the surface, and that's where this hypothesis enters. And then using this sheaf with some other amount of work, you can prove that the induced Fourier-Mukai transform is the derived equivalent. But actually, so this was proved for classical fine compactified Jacobian in a paper of myself, Nero, and Ravagnetta. But the proof is that it uses this guy here. Actually, we prove that these universal things are derived equivalent. So we construct a sheaf here, and so working here has some advantages because the generic fiber are Jacobians, where we know already that the Fourier-Mukai transform is an equivalence of category. So you really need to work with this guy here. But since we have this guy for fine compactified Jacobian V-type, the same proof extends. I have checked that the same proof extends to this case here. And then also other property that they have the same class in the Grothendieck group of varieties. And this follows from the fact that so you have to analyze how this object. So this was again shown for classical fine compactified Jacobian in the paper of myself, Viviani and Schende, and so you and the same. Well, okay, and then you have to check that it works also for these new fine compactified Jacobians. And also, then, if you are over the complex numbers, then there is a perverse filtration you can define by applying the decomposition theorem to this morphism. And there is a formula for the graded pieces of this perverse filtration. And so, let me say like this. So the graded pieces of the perverse filtration. So there is an explicit formula for them, again in the paper with Viviani and Schende, and the same formula work in this case. And so this is so it is independent. There is a formula which is also independent from the chosen stability condition. So the same formula that works for classical, but Jacobian also works here. Yeah, I think my time is over. Yeah, thank you.